This is the third installment of nuclear chemistry. Today we're going to talk about some applications of nuclear chemistry out in the real world. So our first topic is something you may have heard of but not know the difference between: fission and fusion. Both of these are nuclear changes, so the nucleus of atoms are changing, and they are both possible sources of nuclear power. One of them we do use and the other one not so much right now. So main ideas, this is kind of a dividing line between these two. This first picture over here on the left is a picture of fission. The main idea that you need to get out of fission is that a large atom is broken into smaller atoms. Okay, so fission is breaking apart, and fusion sounds a lot like the word fuse, and that's really what it is. It's when small atoms are bound together to form bigger ones. Okay, so again, here's two small atoms bound together to form a larger one. So fission is breaking apart and fusion is building. So fission actually occurs when a neutron hits a large unstable nucleus and causes it to break down into two smaller nuclei. So a neutron is kind of like the starting point here. It gets the ball rolling. So here comes a little bitty neutron, that little white dot, and it hits this great big nucleus that's already unstable. It would undergo alpha or beta decay naturally, but the neutron actually causes it to do something different. It causes it to break down into two smaller nuclei. And the interesting thing is that one neutron hit the big atom and it caused it to break into those two new atoms, but it also released two neutrons. So one neutron caused a reaction that released two neutrons. Well, each of those goes on to hit another nearby atom and produces two each. So we have what's called a chain reaction occurring when the one neutron forms two turn into four turn into eight, and so on. In addition to those neutrons being released, there is a very, very large amount of energy being released. Nuclear fission is highly exothermic, and in nuclear power plants, the energy and chain reaction are both controlled and slowed down so that we can actually harness that energy and do something useful with it. And an atom bomb is the exact opposite situation. Fission occurs and the chain reaction and the energy is completely uncontrolled, completely released, and it happens very, very fast. So our nuclear power plants and atom bombs are actually the exact same nuclear process. It's just whether or not we control it. For fission to happen, you actually have to have enough matter, okay? If the sample that you have is too small, so look at this small sphere over here, the neutrons escape without hitting a new large atom, and so it kind of fizzles out. If you do have enough mass, then the neutrons trigger more reactions. And so this minimum mass that you need is called the critical mass. So like it says, it's the amount of a substance that must be present in order for a chain reaction to occur. One example of this, in the original atom bomb, approximately 100 pounds of uranium-235 was present. Less than that, the reaction again would kind of fizzle out. That would be called subcritical mass. Now, in order for nuclear reactions to be harnessed and a power plant to function, the main idea is we simply have to produce heat, and that heat heats water and produces steam, which turns a turbine. If you know anything about power plants, typically we are heating water to produce steam, which turns a turbine. Normally we would do that through burning coal or natural gas. Of course, other options, you might have hydroelectric power where waterfall turns a turbine, or wind power where wind turns a turbine. But the main idea is you need to turn a turbine. So the fuel in a nuclear reactor, of course, is called fuel rods, and typically it's going to be uranium-235 or some isotope of plutonium. The fancy word for either of those is a fissionable isotope, an isotope that can undergo fission. Control rods are placed in between the fuel rods to kind of control that chain reaction, and these can be raised or lowered into the fuel rods to either speed up or slow down the reaction. So if the control rods are removed, the reaction would speed up, and if the control rods are placed into the reactor, it would slow down the reaction. So control rods can control the speed. A graphite moderator is a piece of the nuclear reactor that slows the neutrons so they enter the fuel atoms, they enter the fissionable isotope, the uranium, at the most effective speed. And again, water is heated to steam. This is the same basic idea as a fossil fuel plant. It's just a different source of heat to heat the steam, and that steam turns a turbine. Now, one key difference in a nuclear power plant versus a fossil fuel plant is the concrete containment dome. So if you've ever seen a picture of a nuclear power plant, there's a big, huge concrete building around the reactor, and basically it just keeps that radiation inside. Remember when we talked about alpha, beta, and gamma radiation, we said that you need several feet of concrete to stop that gamma radiation. So this is just a protection measure around the power plant. Just a couple of interesting historical stories about nuclear power plants. One of the first accidents in a nuclear power plant was actually here in the United States at 3 Mile Island, Pennsylvania. It's a power plant on an island in a river, and there are several nuclear reactors there, and one of them actually had a small accident in 1979, and small amounts of radiation were released into the surroundings, but the accident was discovered and contained before any significant long-term damage occurred in the environment. Unfortunately, we've had two other major nuclear disasters in which they were not discovered in time and they kind of spun out of control. So the first one that occurred was in the Ukraine at a power plant called Chernobyl. This was in 1986. There was an explosion and a fire in the power plant in the nuclear core that released radioactive particles into the atmosphere, and they actually spread throughout much of the then USSR and Europe. And one of the first ways that it was actually discovered was several countries away discovered these radioactive particles in their air, and the Ukraine government hadn't announced to the world yet that this had happened, but it was discovered through those radioactive particles that were basically sent downwind. The area around Chernobyl is still uninhabitable to this day. Nobody lives there because the radiation is still so high. And you may remember a more recent nuclear disaster was in Fukushima, Japan. There was a nuclear power plant on the coast, and there was a giant tsunami, and the nuclear power plant was damaged, and the cooling systems malfunctioned, and 3 of the nuclear reactors melted down and released a lot of radioactive particles into the environment. The thing is, people see these things and they think, oh, nuclear power is bad, we shouldn't use it. Luckily, we've only had, 2 of these disasters in several decades of using nuclear power. Hopefully, of course, we don't have any more, but in general, nuclear power is considered to be fairly safe. All right, switching gears, nuclear fusion. This is the exact opposite of what we just talked about, fission. Nuclear fusion is the process by which small nuclei fuse together to form a heavier nucleus. And this is actually the main process that goes on in our sun and other stars to produce the light and heat that we need. It's very, very exothermic for these small atoms. So in our sun, the primary reaction is that hydrogens are built into helium. So our starting reactants are actually 4 hydrogen atoms, okay? And they undergo a fusion reaction to turn into a heavier hydrogen, and those undergo a chemical reaction to turn into an even heavier helium, and then those 2 heliums bond together to form regular helium. That's our typical isotope of helium there. So the main idea is in our sun, hydrogen, which is the most abundant element in the universe, is built into helium, a larger element. Fusion does also produce a lot of energy, just like fission, and the products are generally not radioactive or greenhouse gases. The product is helium. It's very appealing as an energy source, again, because there's not as much damaging chemicals released into our atmosphere, and it produces a ton of energy. The problem is, to get the fusion started, a ton of energy is needed to get those 2 repelling hydrogen nuclei to move together. Because if you think about it, 2 hydrogens are really just, 2 protons, and we know that like charges repel each other. So it would take a ton of energy to get them to be forced together and undergo that fusion reaction. The piece of equipment that we use to do this is called a thermonuclear reactor. But again, it takes a ton of energy to get started. It's not very feasible as an energy source right now, but it is currently being researched, and there's several engineering projects going on to hopefully be able to create a reactor and help fuel our growing desire for energy. Going back to the stars, a typical star typically builds elements up to and as big as iron and nickel. So that's, only about halfway up the periodic table. Hydrogen's built to helium, helium's built into carbon and oxygen, carbon is built to oxygen, sodium, neon, magnesium, and kind of so on and so on and so on. And eventually we get to like iron and nickel. And these elements kind of arrange themselves to where the heavier elements go towards the middle of the star, and the lighter ones, the hydrogen and helium, are kind of on the outskirts of the star. But a typical star only has enough energy to build up to iron. Beyond that, even the energy in a star isn't enough to fuse, big atoms like iron and nickel together. So the question is, where did our larger elements come from? We do have elements larger than iron and nickel here on Earth. They're on the periodic table. They're normal elements. So where did they come from? Well, they came from exploding stars. So supernova, that are essentially just exploding stars out there in the universe, do have enough energy to fuse even the larger elements together. So anything larger than iron or nickel is actually the result of a supernova. So next time you're holding something like gold in your hand, or tin or lead or some other large element like that, you can know that that element was produced in a supernova. That's pretty cool if you think about it. All right, we're going to talk about uses of radioactivity in our everyday world. They can be used for radiation therapy for cancer. Radiation targets only cancerous cells and can kill them, basically. Radio tracers. So sometimes a doctor might actually have you ingest or inject into you some sort of radioactive isotope that is absorbed by a certain part of your body, and it can help them get images to study your insides. So, one example of that is the nuclide iodine 131, which again is radioactive. Now, notice it only has a short half-life. After 8 days, half of it's gone. But the thyroid in our body actually very readily absorbs iodine. And so after they have injected that iodine 131 into you, they can take an image of your thyroid. So, this is a normal thyroid, and if they see it looking like this, they might know that you have some sort of thyroid disorder. So we have all these isotopes that can be used and are absorbed by certain areas of the body, and can help doctors get images without having to, do surgery or something like that. Nuclear power, of course, we've talked about. Food preservation. Food often goes through a process called food irradiation, where they expose foods to high levels of radiation, and it kills things like bacteria or fungus or insects that might be living on that food. And it'll prevent our food in the grocery store from causing foodborne illness, and it increases the shelf life. Radioactivity is also used in smoke detectors. Now, radioactive elements, of course, long-term exposure can cause damage, okay? This is actually the hand of a doctor that performed x-rays for 15 years without protecting himself. This was very early on in the history of x-rays, and so we didn't really know that we needed to protect ourselves, so it can cause damage. There's two types of damage that can be caused, somatic or genetic. Somatic damage affects non-reproductive body tissues, and it typically is only going to affect an organism during its lifetime. So burns or cancer, if you get thyroid cancer as a result of radiation damage, that's just your thyroid. You're not going to pass that along to your offspring. So that's somatic damage. Whereas genetic damages actually damages your sex cells, like your sperm or your eggs, and that's going to affect your chromosomes, and therefore any offspring that are formed from that sperm or egg have mutations, lifelong diseases, deformities, and things like that. So somatic affects just one generation. Genetic damage is going to affect offspring for many generations. Again, a couple more properties of radioactive elements. They're going to expose photographic film. This is actually how we discovered radiation in the first place. So radiation will cause a photographic film to turn one color, whereas your bones might absorb some of it, and so you can get that image of your bones. It will ionize other atoms, causing them to be charged. So the way that we actually detect if something is radioactive is with this device called a Geiger counter, and it detects ionized particles. So if you have this radioactive rock, it's going to ionize the air around it, and that Geiger counter is going to detect the ions, and it's going to beep and let us know that something is radioactive nearby. And finally, radioactive elements can cause some other substances to fluoresce or glow in the dark. So if you have a regular rock that does nothing spectacular and you put it near a source of radioactivity, it might absorb that radioactive energy and then emit it in the form of light. So it would actually cause a typical looking rock to glow in the dark. So that's all we have for our nuclear unit. I hope this was helpful. Thank you for watching.